Okay. Time to start. All right. How's everyone's what day is it? How's everyone's Wednesday? It's fantastic, I hope. Excellent. Well, today I have one announcement, and that is that your homework is due Monday, 11:59 p.m. After today, you'll technically have everything you need to do all the homework problems. Friday, today we're going over basic related rates, what it is, and then tomorrow we'll be going over a few more complicated problems using related rates. So, but after today, technically, you'll have everything you need to be able to do the homework, okay? Are there any questions about the homework? All right. All right, so today we get into I think, a really cool application of derivatives, and in particular, the chain rule. Participants. There we go. In particular, the chain rule. So in calculus, some people call calculus the calculus of change, because this mathematics allows us to analyze things that are changing in time. Okay, the derivative tells you about an instantaneous rate of change, and so it's perfectly suited to study things that are moving around as time goes forward. Okay, so related rates is going to be our first sort of dive into that realm of calculus. Okay, so in related rates problems, we're always going to be examining situations where there's multiple related variables, okay? And what do I mean by related? Well, like x squared plus y squared equals 1. There's two related variables, right? X and y are related to each other by that equation, okay? And further, we're going to assume that both x and y are themselves functions of t, or really all the variables that we're looking at in whatever situation. We're going to assume all the variables are changing with time, okay? And so the whole idea behind a related rates problem is if I assume all these variables are changing with time, and I know precisely how one variable is changing in time, can I find out how the other variables are also changing in time? Okay, that's the whole idea behind related rates problems. Okay, so as an example, you want to blow up a balloon and you want to fill it up at a constant rate. So in other words, you're putting in the same amount of air every second. You're blowing into this, or you're using an air pump that pumps in, I don't know, 1 cubic centimeter of air every second. Okay, if you know that, then can you say how fast the surface area of that balloon is growing? Okay, and the answer is yes. After today, we'll have all the tools we need, and really technically, you already have all the tools you need to be able to answer this problem and analyze it. Okay, so the best way to look at related rates problems, I think, is to dive right into an example. So here's one of the most basic related rates problems that we'll look at. So we're going to say that the variables x and y are both themselves functions of t. Okay, so really x is, let me change the color so you can see it. This is x of t, and y is y of t. Okay, and we're going to assume that they are related by the equation x squared plus y squared equals t. Okay, we want to find dy dt, the derivative of y with respect to t, when x is 1, and given that dx dt is equal to 2 when x is 1. So let's do this. Oh, I also need to give you, well, we'll get to that in a second. So I have, with all these related rates problems, you want to write down first, what are you given? What are we given? Okay. So what are we given? What are all the pieces of information that we've been given to try and solve this problem? X equals 1. What else? Oh, we got some chats. Yeah, we're given the derivative of x, right? We're given the dx dt when x is 1. When x is 1, dx dt is equal to 2. So that's given. We're also given that x squared plus y squared is equal to t. And this is actually pretty rare. It's going to be very rare in these problems that you're given the relationship between the variables you're interested in. Most of the time, it's going to be up to you to do all the work to figure out the relationship between the variables. But here we're given the relation between x and y. Okay? And one other thing that I forgot to write down is we're going to need to know that dx dt is 2 when x is 1 and y is 1. That's a piece of information I forgot to type in. So when x is 1 and y is 1. We have dx dt is equal to 2. Okay, so that's what's given. And what do we want to find? I'll actually write it out instead of writing WTF. What do we want to find? Yeah, perfect. I want to find dy dt. Specifically at this moment when x is 1 and y is 1. Okay. And equals 1 and y. Okay, so I want, out of all of this information, I want to end up with a dy dt. So how am I going to possibly end up with that with all of these things? I want in the end to have the derivative of y with respect to t. What's the only way I can end up with that with all of this information? What equation? There's not, yeah, it's a good idea. You're kind of on the right track. There's not an equation up here with any dy dt's in there, right? But can I maybe make one from what I have here? How? It was just my tone that told you yes, right? Yeah, I can get a dy dt out of an equation from up here. And the way I'm going to do that, and the way you're like always these related rates problems are going to go, you find your relation or you're given your relation. Once you have that, differentiate both sides of this equation with respect to t. Okay, I want a dy dt out of this. So I should differentiate the only thing that has any y's, I should differentiate that with respect to t. Because again, remember, we're assuming x and y are both functions of t. Okay. So I'm going to take the derivative with respect to t of both sides of this equation. So the derivative with respect to t of x squared plus y squared, this is going to be equal to the derivative with respect to t of t. Well, we'll do the easy side first. What's the derivative with respect to t of t? Oh, we have an answer in the chat.
Isn't that 1?
Yes, perfect. That's just 1. Yes, exactly. That side is just 1. This side, the derivative of x squared plus y squared with respect to t. Remembering that x and y are both functions of t. Okay, so let me write it out over here. D dt x squared plus y squared. We already found the derivative of the right-hand side is 1. So on the left-hand side, I need to take the derivative. Yes, exactly. Someone in the chat said we need to use implicit differentiation. That's exactly right. Okay, these are both, I haven't given you explicitly what these functions of t are, but you do know that they are functions of t. Okay, so I can take the derivative of each part separately. So I'm going to do the derivative with respect to t of x squared plus the derivative with respect to t of y squared. And then the right-hand side is still equal to 1. So remember the implicit differentiation, this is just the chain rule, okay? So if we want, for each of these, we can write out what is the outside function, outside, and what is the inside function. Oops. Outside, inside. The inside function, when I'm differentiating x with respect to t, well, really x squared with respect to t, the inside function is just x of t, because really I can rewrite these as we're assuming these are functions of t. Okay, so the inside function is x of t. Okay. And then the outside function, what's the outside function here? Given a t, the first thing I do is I apply x of t, right? And then what's the last thing I do? What's the outside function? I square it, right? So the outside function is just going to be t squared, right? So chain rule, implicit differentiation, however you want to think about it. I'm going to need the derivative of the outside at the inside. So the derivative of the outside with respect to t is just what? Yeah, I heard it, 2t. The derivative of the inside with respect to t, careful, I'm taking the derivative of x of t with respect to t. And really, that's all I can write. This is just dx dt, okay? And you guys see that with the derivative of y squared, the only thing that's changing is x is becoming y. There's no difference. So this is going to be some scratch work. So this is going to tell me that, well, the derivative of the outside at the inside is 2 times x of t, and then times the derivative of the inside, dx dt. Plus, well, with y, we're going to get the exact same thing, but with a y. 2 times y of t times dy dt. Need to give myself some more room. So there's the derivative of the left-hand side with respect to t. And again, all it was implicit differentiation. But now both functions, both x and y, are implicitly a function of a third variable t. Okay? And then this is all equal to 1. This is all equal to 1. Okay, so x of t, y of t, both changing with time. We don't know what they are, but we know we can differentiate them. Okay. So now that I'm here, what do I do? Because now I have the thing that I want, right? I have dy dt. So what do I do about this x and dx dt and y of t? Let me go back a page so that maybe you can see. What do I do about x and y and dx dt?
Would you be able to simplify the dx dt as just 2 since
Yes.
it's
Yeah, perfect. Exactly right. We want to know what is dy dt explicitly when dx dt is 2 and y is 1 and x is 1. Okay. That's exactly right. So we're just going to plug in all of our givens now. All of our given quantities. Okay. So I'm interested in dy dt when x is 1. So I'm going to get 2 times 1 times dx dt is 2. Plus 2 times y is 1 times dy dt. Well, that's just what we're trying to find. And then this is still equal to 1. We have a question in the chat. It should be t of x equals t. No, x of t is implicitly a function of t. The x and y are both separately functions of t that are related by this equation. Okay. So from here, now I have an equation that only has a dy dt. So what should we do? Yeah, just solve it, right? So 2 times 1 times 2, that is 4. Plus 2 times 1 times dy dt, well, that's 2 times dy dt is equal to 1. So that tells me subtract 4 from both sides. I'm going to get 2 dy dt is equal to minus 3. And that tells me dy dt is equal to negative 3 over 2. At the moment that x is 1 and y is 1 and dx dt is equal to 2. Okay. Are there any questions? Question in the chat. Is this a proof or a problem that could be on exam? Yes, absolutely. This exact type of problem could definitely be on the exam. I wouldn't call it a proof per se. This is just an application of implicit differentiation. But yes, this type of problem would definitely be on the exam. So dy dt is yes, yeah.
I have a question.
Yeah.
For the derivative
Yeah.
of the equation, would it be incorrect to write it just as 2x dx dt?
No, not at all. No, not at all. That's actually what I will do most of the time.
Okay.
Yeah, writing out, I only did it explicitly here to make it very, very clear that x and y are functions of t. But yes, the question was asked for anyone online who might not have been able to hear. Once we got to here, you could write this just as 2x dx dt plus 2y dy dt is equal to 1. You don't really need to explicitly write x is x of t and y is y of t. That's just, I was just making that explicitly clear so that you could see when we were taking the derivative what was happening. Excellent question. Any other questions on this? Because the problems, just so you all know, the problems will get more complicated, kind of, but in theory, this is really all related rates problems boiled down to what you need to do every time, okay? The only difficulty is you're not always going to be, and in fact, you will almost never be given the relation between x and t, or sorry, x and y. Okay. So the question was asked, why did we apply the derivative with respect to t to x and y in the first place? Again, we assume to start that x and y are functions of t. So that's what we're assuming now. So x and y could be your position horizontally, a position function horizontally, and a position function vertically. Those are both changing with time, right? As you run, you can jump, and those aren't really, those are both functions of time, right? Another thing, the first example I gave, as you blow up a balloon, the air going in, the volume, that's changing in the balloon, and also the surface area is changing with time. So those are two variables that are related, but they are changing in time separately. Okay, so with all of these types of problems where particularly time is involved, we're always going to assume that all the variables involved are functions of t. So, do you have any more questions? Because I do get that it's a sort of, technically it's not new, again, just implicit differentiation, but it's definitely a new wrapping paper. I agree with that. All right. So let's look at one more example like this. Assume that x and y are both differentiable functions of t, and that x times y is equal to 4. So again, this is very, very, very rare that I would give you the relationship between x and y. Okay. We want to find dy dt when x is equal to 8, given that dx dt is equal to 10. So, what are we given? Given. What information did I give to you?
X equals 8.
Yeah, we're interested in this thing when x equals 8. What else? Perfect. We also know dx dt is constant 10. Okay. Is there anything else?
X times y equals 4.
Perfect. We are also given this relation x times y is equal to 4. That's all you've been given. And what do we want to find? Exactly, dy dt, in particular when x is equal to 8. Okay. So, one thing you should never do, I know some of you are going to do it on the homework because it seems like it makes it way easier, but it makes you wrong. One thing you should never do is plug in x right away into here and then take the derivative, because that's wrong. That's going to give you the wrong thing. Both x and y are changing in time. So we have this thing that's changing in time. We want to take the derivative to find out x prime and y prime, and then only after that we care about this at the instant that x is equal to 8. Okay. So I want to get a dy dt out of something up here, and so what should I do?
Multiply both sides by d dt.
Yeah, exactly. I need to apply the derivative, d dt, to both sides of the relation. And again, that's always going to be the case for these related rates problems. Once you have the relation, or you're given that relation, you're going to differentiate with respect to t. We'll do the easy side first. What's the derivative of 4 with respect to t? Careful. The derivative of 4 with respect to t. Oh, do we have it in the chat? 0, yes. Oh, someone asked, can velocity and position be y and x for this concept of changing with time? It depends. In this context, no, x and y are just general variables, but that's going to depend on the problem, okay? So, but dt of 4, the derivative of 4 with respect to t is just 0, because it's a constant, okay? So now we need to look at the derivative with respect to t of x times y. How am I going to take the derivative with respect to t of x times y? Derivative with respect to t.
Product rule.
Yes, perfect. This is, I said times, right? X times y. So this is the product rule. These are both functions of t. So the product rule says take the derivative of the first thing and leave the second thing alone. So the derivative of the first thing, x, is a function of t, so that's just dx dt. Okay. And then I'm going to leave the second thing alone, times y. Plus, then I'm going to take the derivative of the second thing and leave the first thing alone. So plus the derivative of y with respect to t, well, we're just writing that as dy dt times x. Okay. So there's the derivative of the left-hand side. So putting it all together, after we differentiate our relation with respect to t, we have dx dt times y plus dy dt times x is equal to 0. Okay. And now, what should I do?
Plug in your givens.
Plug in my givens. So I'm given x is 8, dx dt is 10. So dx dt is 10. I wasn't given y. Plus x is 8, dy dt equals 0. So, it seems like I don't have enough information. But my tone should obviously tell you that we do. So, I want to know dy dt just as a number. How am I going to find out when I have this y floating around here? Oh, perfect. Yes. Someone in the chat says use the relation. We know that x times y has to be 4. Okay? So when x is 8, then that means 8 times y is equal to 4. This relation, x times y equals 4, has to hold for all time. That's what we're saying when we write down that relation. That these are both functions of t, but this relation always holds. Okay? So 8 times, when x is 8, we have 8 times y is equal to 4. So y is equal to 1/2 when x is 8. Okay? But that's exactly the case we're looking at right now. So I'm plugging y equals 1/2 in right here. So I get 10 times 1/2 plus 8 dy dt is equal to 0. And now I can just solve for dy dt. Because this tells me 10 times 1/2, well, that's 5. And then plus 8 dy dt equals 0. That tells me 8 dy dt is equal to -5. And that tells me dy dt is equal to -5 over 8. Okay. Any questions on that? Really, this example encompasses really everything. Because sometimes it will seem like you don't have enough information, but any information you don't have, you'll always get from the relation between your variables. Okay? So every single problem, once you boil it down, is going to look something like this. It could be in the form of a word problem, but once you extract the proper information, it's going to go exactly like this problem went. Okay? Any questions on this example? All right, we'll look at one more slightly more complicated problem and then go over some general guidelines for these types of problems. So, a pebble is dropped into a calm pond, causing a circular ripple. The radius of the ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the water inside the ripple changing? Okay. So, this is a word problem. You haven't been given the relationship between any of your variables. So there's a little bit more work involved, but once we get a few things written down, it's going to go exactly like the last problem went. Okay. So with these word problems, you're always going to start with a sketch of what's happening. Okay. So I drop a rock into a pond, and then that creates a circular ripple that looks like that. Okay. I drop the rock right there, and then this radius, which we're calling R, I'm not going to put 4 there because the radius is changing with time. Okay. So that radius is R, and that is changing with time. It's growing, right? And then the area of this circle is what? Who knows the area of a circle of radius R?
Pi r squared.
Perfect. A is pi times R squared. I know what you're going to ask me. Will I be given this formula on the exam? The area of a circle, probably not. If I think there's a related rates problem on an exam where the relationship might not be immediately known to you, then I will give you the formula. But you do have to know the area of a circle. Okay, so pi times R squared is the area of a circle of radius R. Okay, so what have we been given? This drawing is good enough, right? Because as long as you label that radius with R to indicate that it's changing, then we want to find out how big that blue area is growing, right? So what have we been given in this problem? What have we been given?
Would we be able to assume that since the ripple is circular, that the equation would be x squared plus y squared equals r?
We could use that equation, and that's a very good point. There will be times where there are competing equations that you might want to use. I'll say for this one, x squared plus y squared equals r squared is not going to be the most efficient way to do it. But that is a good thought, and it is good to know multiple equations that might come into play. But for this one, so think about, we want to relate the area and the radius, right? And we've actually already done that right here. Because we want to find out how fast the area is changing. if we know how fast the radius is changing. So this isn't given, but it's going to be important. I'm going to rewrite a equals pi r squared. That's going to be our relation that we care about here. What else have we been given? Yes, someone said the rate of change of r. We're given the rate of change of r. How can I write that the radius of the ripple is increasing at a constant rate of 1 foot per second? How can I write that using math symbols? That's going to be a big part of these.
Is it dr by dt equals 1?
Perfect. The rate of change of r. That's dr dt. If you ever write down dr dt, you can say word for word, that means the rate of change of r with respect to t. And t is time for us. And we know that the rate of change of r with respect to t is just the constant 1 foot per second. If you want to write the units, I'm just going to write it as 1. Yes, perfect. And then are there any other givens for us?
R equals 4.
Yes, exactly. We care about this whole situation at the moment that r is equal to 4. Okay. So those are all our givens. What do we want to find?
dA dt.
Perfect. dA dt. dA dt. Specifically when r is equal to 4. Exactly. All right, guys. And now, I mean, if you ignore all this stuff now and just focus on all the stuff we have written down here, it looks exactly like the problems we did before. We have the relation, we have how fast one of our variables is changing. We can find how fast the other variable is changing. Okay, so the biggest part of the word problems, and it's always the biggest part of the word problem, is translating everything into math terminology. But once you've done that, these problems all go the same way. So now, what should I do? I want to get a dA dt. So what should I do?
Multiply both sides of the a equals pi r squared by d over d.
Yes, exactly. Yeah, so just to be clear, whatever helps you guys remember this step, I'm for. I'm not technically multiplying by d over dt. I'm applying, when I write that, that technically means I'm applying the derivative. If you want to remember it as multiplying by d over dt, whatever helps you remember. But just know that that's not technically true. I'm applying the derivative. So on the left, what do I get? A is a function of time. So when I take the derivative of A with respect to t,
Is it 0?
no, it's not 0, because if we look back at our drawing, this circle is expanding, right? So the blue area is definitely increasing. So the derivative of A with respect to t wouldn't be 0.
dA dt.
Exactly. It's kind of a trick question. The derivative of A with respect to t, well, that's what we're trying to find, right? dA dt. So we just write it down. Okay. And then the right-hand side. So what's the derivative of pi r squared with respect to t?
Would it be 2 pi dr dt?
So close. 2 pi times, not dr dt. It's so close, though.
It's 2 pi r
Yeah.
dr dt.
Perfect. So remember, the r is actually and the inside function because r is r of t. Okay. So that's why we get 2 pi r dr dt. Okay. And then once we're here, after you've taken the derivative, then plug in everything you know. Don't simplify, plug in everything you know first. Okay, then simplify. So dA dt, which is what we want to find, this is equal to, well, 2 times pi, that's just constant, times r. We care about this at the moment that r is equal to 4. Okay, so 2 pi times 4 times dr dt. Well, dr dt is just 1. Okay, so dA dt is equal to 8 times pi. So, looking back up here, if I hadn't given you an r value, if you only knew dr dt was 1, this still tells you useful information. If you know that the radius is increasing at a rate of 1, then the area is increasing at a rate of 2 pi r. So whatever the radius is, or sorry, the area is increasing at a rate of 2 pi r. So whatever the radius is, the area is growing faster and faster the bigger the radius gets. So even though the radius is increasing at a constant rate, the area is getting bigger faster. Okay, so that's a pretty fun little fact. So, but all of that to say that our final answer in this problem is dA dt, the rate of change of the area, is 8 times pi. So is this area growing or shrinking?
Grow.
Yeah, it's growing. And it's always a good idea to draw it. With the drawing, I know that the circle is expanding. It's obvious that the area is growing. The sign of dA dt will also tell you whether something is growing or getting bigger or shrinking, right? If dA dt had been negative, that would have meant that that the area was actually shrinking. And that would have been an indication that maybe we did something wrong because the area should clearly be growing. Okay. So can we say that this relation has no relation to the slope concept for the two variables? No, that's not true. It's just the only thing is with the chain rule, or sorry, with related rates, we don't ever have an exact idea of what x and y are. So we can't say for sure what the tangent line looks like, but we do know the slope, the dx dt and dy dt, that's still the slope of x and y with respect to t. Okay. So here are some guidelines for solving just general related rates problems. All these problems we've seen, they cover everything. That, again, nothing will be new now. You might be asked to find maybe dr dt given dA dt, or you might be asked to find different things or to find new relationships, but the mechanics of these problems are always going to be the same. Step 1, you're always going to identify all the given quantities and all the quantities that you want to find, the quantities to be determined, okay? Specifically, you should find all the quantities that are changing with time, okay? You're going to make a drawing. Make a drawing. It's in red because it's important. Make a drawing when possible, and then label the quantities in your drawing, okay? Step 2, you're going to write an equation relating to variables whose rates of change are either given or you want to find. Okay, so for this last problem, the equation we wrote down was A equals pi r squared, because r was changing with time, and we wanted to find out how A was changing with time. So we wrote down an equation relating those two variables. Okay. If your equation has other variables in it, that might be a hint that you're on the wrong track in trying to find a relationship between the variables you care about. Okay. Step 3, use the chain rule to differentiate both sides of the equation you found in step 2 with respect to t. Okay? With respect to t. Okay. But that's implicit differentiation, really. And then once you do that, you substitute all of the things that you know about all the quantities, and then solve for the rate of change that you want. Okay? But you only plug in the numbers that you know after you differentiate. If you plug them in before, you're going to get the problem wrong. Not just because that's not the method that I said. No, you're legitimately doing it wrong. And if you plug in something that is, if you plug in a constant number for something that's changing with time, and then you differentiate, you're going to get 0 from that, right? If something's changing with time, you have to differentiate first, then plug in to see how it's changing with time at that moment. Okay? So these are the 4 steps. Every related rates problem, every single related rates problem, you're going to go through these 4 steps. Okay? It's never going to change. Okay. So an example, inflating a balloon. Air is being pumped into a spherical balloon at a rate of 3 cubic feet per minute. Find the rate of change of the radius when the radius is 4 feet. Okay. So step 1, I need to identify all given quantities and quantities to be determined. So given quantities. Oh, you know what? I'm gonna have to stop at a weird spot. Okay, we'll pick up this problem tomorrow. I'm gonna draw the spherical balloon. Your homework, small homework problem, is make sure that you know the volume of a sphere for tomorrow. Okay. Okay. If there's any questions, you can stick around and ask. Otherwise, please wipe down your desks before you head out.
Thank you.
Thank you.